Right. So I'm going to be talking about what I think of as a compositional theory or account of what's known as active inference. And I believe, along with a number of people, that active inference encapsulates the process by which things like intelligent systems learn about their world and effectively learn to survive in their world. And of course, that means they need to learn explanations of the things that they encounter in their world. And I think of those kinds of explanations effectively as right abstractions. A good explanation is something that allows you to summarize your incoming data, which is much like an abstraction, it seems to be. So first of all, I'll give a bit of background. My background personally is in computational neuroscience. Although I've had some formal training, I'm a default student in the psychology department at Oxford. I've gone quite rogue by doing so much category theory lately. And the reason that I did that was that I was dissatisfied with the mathematical structure of computational neuroscience more generally. So I wanted answers to questions like, how do models relate to each other? How do they plug together? And how do we understand that resulting model? How do we translate ideas and concepts between different research groups? And how can we stop reinventing the same concepts all over and over again? And I realized, after not much investigation, that I was seeking effectively a compositional lingua franca, something sufficient to express common patterns, translate ideas, and connect things together. And of course, something like category theory, in fact. So today, I'm going to tell you some of the things that I've learned about what I think of as the structure of learning structure. I'm going to emphasize compositionality, and that really means taking interaction very seriously. And so I'm going to sketch the beginnings of a news story in fields like computational neuroscience, effectively a kind of cybernetic story, to answer questions like, how do adaptive systems find abstractions? How do things learn anything? How are the resulting beliefs structured? And do we ever have more than consensus? At Topos, we're interested in telling such kinds of news stories for all kinds of systems, interconnected systems particularly. And so we seek a new interconnected scientific ontology. And I'm sure that that's going to be really important in human flourishing and things like AI alignment. I'm with Valeria on this. I think we need to seek AI alignment for the artificial intelligences that we already have, things like corporations and social systems, and we should be concentrating on those right now. And I think I and the rest of the Topos Institute hopes that acknowledging interaction should promote sustainability of human society on Earth. Okay, so we're going to start with a kind of review of the familiar stuff. What makes the world compositional? In particular, I'm interested in spaces and the things that are living in those spaces and what makes them living things. So, of course, the world is really complicated, and so are the things within it. But at the same time, it does seem to be, more often than not, made of things plugged into other things, connected together. And so it seems that if we are to have any hope at all of understanding the complexity of the world and the complex systems that we've built in it, we might as well make use of this latent structure, which we seem to observe. And I think that's what the brain does all the time by observing patterns. And effectively, isn't making use of latent structure what right abstractions are all about? So we know this quite well, I suppose, that categorical, or more broadly, compositional structures are everywhere. We've got maps of the world, dynamical systems, topological spaces, logical statements, neural circuits, natural language statements. I don't need to list the rest of them. They're all over the place. I think it'd be really interesting to find something that was a kind of interesting system or phenomenon which didn't have some compositionality to it. And in particular, the kinds of systems that we're often interested in studying compositionality are things that we could think of as open systems, because they have a kind of obvious way of being plugged together. But even things that might not look open could be divided up, and so it might admit some kind of compositional description. So I'm sure that taking connectedness and compositionality seriously means really acknowledging two related things. that systems interact and that therefore their behaviors are context dependent. And we have to take this context bit seriously too, because only tautologies are true if you don't make any assumptions, if you don't have a context. Now, I'm sure most of you know that the fundamental theorem of category theory, Yoneda's lemma, says that, roughly speaking, the way that a thing connects to others and itself determines the thing itself. And this comes up everywhere. There's the maxim of the linguist Firth, who says, you shall know a word, and this applies equally to places or concepts, by the company it keeps. And that applies too to our abstractions, our models, and the stories they tell. So I want to tell a particular story about things, living things in the world, in the space that is the world, the space, the stage on which events occur. And space itself is compositional because we can glue bits of spaces together. For instance, think of building an apartment block. You're kind of gluing floors one on top of another. Or more abstractly, here on the right, we've got a picture of a simplicial complex, and that's a kind of cellular space made by gluing smaller, or more simple cells together. But spaces are kind of more than just the collections of points glued together. There are also paths between the points, and I've drawn a kind of space here with some paths between them. And so we can think of spaces in a kind of categorical language, categorifying them accordingly. Paths in the space become morphisms. The morphisms tell you how to get from one place to another. And sometimes you can go in both directions along a path, sometimes it's directed, but the key idea is that paths are like morphisms rather are like paths in some space. And this points the way to what is called topos theory. Topos is kind of like a nice categorification of a space with some kind of nice logic, which I'll talk about momentarily. So there are various notions of topos. The kind that I'm talking about is formally called a Grothendieck topos, but I think you should think of, roughly speaking, any kind of thing that's called a topos as a kind of categorified space. And we can sometimes divide these topoi into two kinds, big and small. And in a big topos, we can think of the points, the objects of the topos, themselves as spaces. And the paths in the topos, the maps, are kind of maps between spaces. So if you think of like this picture on the left as being some diagram in a topos, you can kind of zoom in on these objects, which are themselves spaces, and draw what the maps mean. That's these kind of light gray lines on the right. Yeah, and think, when I'm moving around this space, I'm mapping points and spaces to other points. Okay, well, that's a nice story. So what can we do with this? Well, we'll see later on something that we can do with this. But first of all, we need a bit more theory. So I want to talk a bit about slice categories. So the slice over an object in a category, let's think of the sort of middle object on the left, this space with these 3 dots in it. So the slice over this X is the category of objects that map to X. And this, in topos theory, gives you another topos. And it's the topos in the context of X. Its objects are what are called bundles, like this picture on the right. This is kind of version of this map on the left here. And a bundle represents something called a dependent type. And it says that for each point in the codomain, we get a collection of points in the domain of the map, which is given by pulling back where the map takes you to. So for instance, with this point on the left, it gives you this set of points. There's 2 points on the left here. And these things, we can think of them as like abstract dependent types with a context. We can think of things like, we can think of the base, this sort of codomain object, which we call the base of the bundle, or the base of the dependent type, as like a place. And the types above it, where we pull back these points to, they say things like they're the stuff that can happen in each place. So an example I like to use to think about dependent types and bundles is like a weather forecast. the kind of weather forecast you get depends on where you are on the Earth. For instance, if you're on land, you might care about things, simple things like whether the sun is shining or whether it's raining or the temperature. But if you're over sea, you're probably on a boat and you might care a bit more about things like the tides or more information about the wind pattern. And so this type, the weather forecast type, depends on where you are in the space. That's what makes it a dependent type. But more generally speaking, any sheaf, for instance, like David Jowes was talking about before, gives you a kind of dependent type. We can think of dependent types in the same way as attaching data onto points of the space. Here, you're attaching these data spaces to the points of this base space. And what another thing that we'll come across, and that David Spivak has talked about, polynomial functors. They're also a kind of bundle. So it's good to sort of get that theory down because we're going to be talking about them a bit now. But before I do so, I want to talk a bit about what's known as the internal language, what you can say if you just stay in the world of a topos. So the internal language is like a kind of logical language. You can write down propositions about the objects and morphisms, or the types, as it were, in the topos. And this logic is higher order. You have conjunctions and disjunctions and implications and quantifiers that say things like, there exists an X such that Y, or that for all X. Each topos has a special object called a subobject classifier, and this assigns truth values to propositions. And these truth values in a spatial topos are kind of like roughly saying something like where a proposition is true. For instance, if you have the proposition, it's sunny, that's only true in the places that it is actually sunny. And so the truth value, true or false, varies as you move around the base space. And in a topos, of course, as I've mentioned, we can construct dependent types in this internal language. The base of each bundle gives us a logical context. We can think of this as saying something about the axioms we impose. This is what I was referring to earlier. The assumptions you make about the structure of the space. So what bits are connected to what other bits. For instance, which land masses in the weather forecast example are connected to which others. And so changing our assumptions or the context corresponds to moving around the base space or changing the base topos. For instance, as kind of tectonic plates move around on the surface of the Earth. Okay, so that's a bit of logic and a bit of I don't have time to go into an awful lot to talk about, and I want to get onto living things and their internal models. I think some great examples of things come from biology. We're too familiar, it seems, with kind of artificial things, which are simple and often not interconnected. But biology is full of really interconnected examples. So we've got cells, obviously, that are really like thingy and connected to other things around them, and that their behavior depends on what's around. But more, kind of lower level, we have enzymes and proteins which have great shapes and that interact by sort of plugging together in the same kind of way that computer networks plug together, it seems. But these change their shapes. And of course, we've got things like neurons, and they form the neural circuits that I started with. And we want to talk about how these things are connected, and so we're going to try and put some sort of formal compositional language onto that. And so I'm going to adopt polynomial functors for this, and this is thanks to David Spivak introducing me to them. Okay, so I'm going to start with these things, which are basically like wiring diagrams that describe how things are connected up. And you can read these from left to right, and you can think of that as going from something like input into output. And I'm going to use this funny notation, this kind of polynomial notation at the bottom, to describe the boxes and the wiring of the boxes to other boxes. So this box on the left is a box from Z inputs to C outputs. I'm going to write that as C times Y to the Z. And we can make this a bit more complicated. Here's one that has outputs in BZ and inputs in YC. And now the morphisms of polynomials are going to be ways of wiring things together. So here we've got two systems. The two systems I've drawn on the left. and we put them in a box next to each other. And putting things next to each other corresponds to doing this kind of monoidal product, this tensor product thing here. And that is a monoidal product structure on the category of polynomials. And wiring these two boxes together and to this outer box is a morphism of polynomials. For now, it doesn't matter precisely what the...
Toby, so
yes.
You're saying... So I'm just looking formally at this, right? So the tensor is actually like wiring up the z of the one with the z of the other. Is that right?
The tensor is just putting things together. It just puts the bz and the c next to each other in the coefficients, and the z and the yc next to each other. It's just like doing product in the coefficients and the exponents. And then the wiring is what's done by this polynomial map.
Why are they doing this polynomial notation? Is this supposed to suggest something?
Yes, it's both supposed to suggest the exponential structure in a category where we write the set of maps from z to c as the exponent c to the z, and it's formally the case that this y is like representing this kind of representable functor, the functor of maps from z, rather from z to something else. It's a Copri sheaf. And so formally they work out in this kind of same exponential way. But for now, we can just think of these things as like notation. But yeah.
Okay, but I'm trying to understand the notation. So I tensor them, so I just put them parallel next to each other. They're not connected. And now you're saying this map that there's some sort of map to BYY, and this is gonna wire them up, or like what is the wiring information? Where's that?
The wiring information is encoded in the morphism of polynomials, which says how you take the outputs to outputs of the outer box, and how you take the inputs to the inputs of the inner boxes, and at the same time, it effectively says where the inner boxes get their information from.
But I find this weird because if I have, I suppose you can have multiple z inputs or something, right? How do you know that this z has to like wire up with that specific z as opposed to just another z?
All the exponents are indexed by position in the base by effectively a coefficient. So this is like the thing on the left here, the cy to the z is like c times y to the z. So it's like y to the z plus y to the z plus y to the z c times. And so for each point in c, you get a z. And so that gives you an indexing.
Thank you.
Okay. But this is just a, it's good to get this sorted, but it's just like a little example for now. We're gonna get a bit more complicated, but we don't need to talk about all the details. I'm just trying to tell a story. And if we want to do the kind of formal stuff, we can talk about that later on. And in particular, this stuff can get much more sophisticated, and these polynomials can talk about things like the shapes that can change. But for now, I want to talk about how we know what stuff is out there. How do we even start to talk about finding the right abstractions? Okay, and so for this, we're going to talk about models, and statistical models, and how they are updated. I like this idea of elan vitale. What is the animating spirit or force that gives things in the world life? How do we talk about that formally? And so more precisely, I mean, what is the structure of an agent or a thing's internal model? You look at a thing and, inside of it, somehow, maybe it has a way of predicting the world. And what is its structure? And what makes that structure possibly modular? Like we think maybe the brain or mind seems to be modular. And how do the models that we have of kind of in these systems, how does that relate to their forms and their interconnection? Okay, and so for this, we need a bit of categorical probability theory. I don't want to spend an awful lot of time on this because, again, I'm just trying to tell a story, but I think it's important to get the terms that I'm using clear. So I'm going to be working in what's known generally as a Markov category, which is basically like an abstract place that you can do probability theory. In this case, the objects of the category are going to be spaces. The morphisms are going to be what I call stochastic channels. And we can think of these as conditional probability distributions. They say, given a point in X, I get a distribution on Y. And so that's saying okay, given some X observation, what is my Y belief, or my condition, my probability of events in Y conditioned on observing X? They're the same thing. There are these things called states, which are just going to be distributions on a space. And those are channels out of the monoidal unit, which is typically going to be the kind of trivial space with one point. And although I'm not going to write much probability notation, I'm going to adopt this kind of standard notation where if I have a channel from X to Y like this, I'm going to write the probability assigned to a point Y given X as P of Y given X, even though really formally it's a function applied like P of X of Y. Okay, and then you can compose these things, and this composition of these conditional probability distributions, these stochastic channels, is given by averaging over the type in the middle of the composition and sort of marginalizing it out. We can think of that as kind of pushing forward uncertainty along these channels. Okay, I'm going to draw some diagrams, not many diagrams, but I do want to talk a bit about Bayesian inversion and joint probability distributions and what people call generative models. And for that, I find these diagrams quite intuitive and helpful. And so I want to talk a little bit about those first. We can draw these things with kind of multiple wires coming out, and they serve two purposes. One, they serve to describe the kind of causal structure of something like a generative model, because we can think of the information as flowing from the bottom up through the model. But they also describe how the model factorizes. And so we can, we can decompose some joint distribution into a prior and a likelihood on its likelihood on one of its marginal spaces, and we can draw this kind of product rule like this.
Very tough.
Yes.
So okay, I think I understand X, Y. The wire next to each other. That's a tensor of two objects.
Yeah.
And
so it's like the
this
joint space.
Yeah, exactly. X tensor Y, right? That's what this is saying. But then the triangle, what is that? The triangle W.
Is just notation that says there's a trivial space here, and so it picks out a distribution on some space, because a map from a trivial space into some other space is just an element of that space. In this case, the space is distributions on X, and so this is just a distribution on X, and we can think of that as the prior of this model here, or the equivalent of the X marginal.
So no, but I'm sorry, still confused. So I have X tensor Y, and I'm mapping to D of 1 or something. Is that what you're saying?
I don't know what D is.
D is the Kleisli, the set of probability distributions.
No, we're reading from the bottom up.
Oh. Okay. So I'm going from I to X tensor Y. Is that correct?
So it picks out a joint state, right? So that is like a distribution on X times Y. And that joint state is factored because of this probability, product rule and probability that says you can factor a joint state into a prior and a likelihood.
Right. So what is the dot, like categorically?
Oh, this is just multiplying numbers. This is me saying I don't like the way people write probabilities, and so I'm going to write it in diagrams. But...
No, the dark dot.
Oh, the dark dot is okay. So it's a copier in the category. It's like the canonical morphism on a comonoid structure. The comonoid,
okay,
which is X.
Okay.
And this is just saying this joint distribution factors like this. It's just notation. But I also like to think of it as describing the information flow. But I want to make progress. I need to make progress.
Okay.
So we've got marginals we can throw away, and we get that by throwing away one of the wires. We can throw away the right wire to get the marginal on the left, which is just pi, and we can throw away the left wire to get the marginal on the right on Y, which is C after pi, which is this thing which we normally write down as sum over all the x's C of x given Y times pi of x. I mean, that's what this thing says here. That's the other marginal. Okay, we can write down Bayes' rule. It's a way of kind of translating between two different represent decompositions, disintegrations, or a product distribution. It says that I can go from a channel from X to Y, a conditional probability from X to Y, to a channel from Y to X that says, given some Y observation, what should my prior belief have been, or how should I update it? And it satisfies this rule, which is, again, just another version of the product rule in probability theory. It has this nice graphical form. It has this nice kind of symmetry.
So are you saying that this base rule endows the Markov category with some sort of dagger structure?
It does, in a sense, it endows the slice under the terminal object with a dagger. Yes.
Okay.
But the key point I want to make is that it's not just a dagger on the category itself, because it depends on the prior, right? You don't get a channel unless you know what your prior was. You need to choose a prior in order to find an inverse channel.
But it's actually on the undercat or the co-slice category.
It's a dagger on the co-slice category, but I'm just using the dagger notation because
interesting. Okay.
Yeah, and that co-slice category says that fact says that we need a prior, and that's the key point that I want to make now. Given a generative channel that says, given some prior belief, I make observation in Y, the recognition channel that goes in the opposite direction depends on the prior and has this type. It has a prior on X times observation in Y, gives me a new belief on X. And so we compare these forwards channels that make predictions with these update maps, with these kind of dependent update maps. That pairing is called a lens. They're all over the place. They encapsulate what David Jazz is calling hierarchical planners. And we can prove, and I'm not going to prove it now, they can look it up, that the inverse of a composite channel that says, okay, so say you're like at the cinema, you're trying to predict the cinema screen, but you can only look at a little patch of the screen, then you make a prediction about, the whole image, given predictions of the patches. You've got a composite channel that does that, and you can update your belief about the whole image, say this kind of latent belief, by first updating your belief about the patch, which is the thing you're looking at, and then using that updated information to update your belief about the whole picture. And that might be how the brain does updating complicated scenes. And it's quite nice because this is, in some sense, a right abstraction, because this compositionality property seems to match up nicely with the kind of compositional structure that we see in the cortex, where we've got these kind of local circuits which do sort of Bayesian updating of kind of component channels. But I'm not talking about that today. I'm only saying that we can do Bayesian inference in a nice compositional way, and that it has this structure. I'm not going to walk us through these diagrams. It's something that we can come up to, but each of these boxes is one of these lenses, a pairing of a forwards and a backwards channel. And this just says that we can compose the forwards channels and backwards channels according to the lens composition rule, which says that, okay, the composite of the joint of the inverse rather of the composite channel is just given by the composite of the inversions according to this rule. It says, first of all, you invert D, you have to use the information predicted by C, and then you can push that through the inversion of C. So you kind of go in the opposite direction, which is kind of what you'd expect, because you're sort of going, making predictions from causes out into observations, and then you have to go back from observations up to causes. And so it has this kind of backward structure. Okay, these are the things that I'm going to call Bayesian lenses, and they formalize what I like to think of as hierarchical, like predictive models. But the structures I was talking about just then are kind of exact inversions, and obviously, yes.
Could you say what you mean exactly by Bayesian lens? What is the definition?
A Bayesian lens is a pair of a forwards channel or condition probability distribution, and one of these backwards channels, which takes in a prior and gives you the updated prior and given an observation. Okay,
so that there's the forward channel from X to dy, is that right?
Yeah.
So it's like an index, it's like a family of distributions on Y, right?
Yes. Yes.
And then you're saying, so what is is that a prior? Is that what you're saying?
No, the prior is the thing that you supply to get the distribution on Y. So you get, say you've got a distribution on X, that's what I would call the prior.
Okay, so I have
that channel.
So I have a distribution, a prior on Oh, okay. So I have like I have like a whole what I call W earlier. I have like a whole parameter space.
Yeah.
That is an X is the parameter space of distributions on Y, and then I have a prior on that, so a distribution on that, and then given a Y, a point in Y, it updates all these. Yeah, okay, it updates
It does
this
the
prior.
Bayesian inversion. Yeah,
Right.
That's right.
Okay, and
Yeah.
this is what you call Bayesian lens. Okay, cool. And
Yeah,
then
lens is
these
this
form
pair.
a category.
This forms a category, and they compose according to this lens composition rule,
Right,
which I'm not going to talk about because I'm
Right.
just saying that it exists and the rule is here. But
Right.
I need to.
Okay, that's very cool. Thank you.
I need to make some progress again because those are exact lenses, and systems in the real world typically can't do exact inversion because it's too computationally difficult. We can only do approximate inversion, and so we want to talk about how well a system does at this inversion, right? There's a lot of freedom in choosing an inversion in approximation. We could choose the trivial approximation that just picks out the same distribution as the prior all the time, and that would be really rubbish mostly. It would be right sometimes, but mostly rubbish. So we want to quantify how fit or the fitness of an approximation scheme, and that depends on how the system interacts with the world. It depends on two things, the prior and the environment that the system is in. So the approximation is, as I say, context dependent and parameterized. Well, we can talk about the parameters later, but I'm going to focus on the context. So I'm going to make this category of what I call statistical games. And I call them games because you can think of the system as playing the game of trying to maximize its performance at making predictions about the world. So the category is going to have morphisms, which are the same as the objects of the category of Bayesian lenses. So that's pairs of spaces. Often it's just the same space twice. And a morphism is going to be one of these Bayesian lenses equipped by a loss function, which takes contexts, which I'll define in a moment, into real numbers that say how good the system is at doing the prediction. So these contexts are everything needed to make this lens, which takes inputs and gives outputs, everything needed to make that open system a closed system. And so that's going to be, so we think of the closed systems as ones with trivial inputs and outputs. And so that means I'm going to have a lens from ones and into the domain type and a lens from the codomain type into ones. And you'll just have to trust me on this, but that works out to mean a prior, so a distribution on X for a lens of this type, and what's called a continuation. So this says, given some predictions about Y, I make some observations in B. And typically Y is the same, but it's saying, what observations or what data does the environment give the system? Okay, and then we compose these things given using the lens composition rule, and I just say we just add up the fitness function. So I mean that doesn't matter. Okay, so then we can formalize lots of kind of like statistical tasks in this setting. Maximum likelihood estimation, for instance, corresponds to Bayesian lenses with kind of no inputs, no priors, and just a state, because they're saying, okay, I make a prediction about my data set, and I'm trying to change the parameters of this prediction of this distribution I've got in my head in order to explain the data better. So I have just a state, a distribution, and I have some data, which is just this thing given by the continuation. And I'm trying to say, here's my loss function. It's saying maximize my likelihood. And we can think of this likelihood function, this log probability function, as in the following way, right? So like we can think of this density, this P, that's given by the pi state or state distribution, as measuring the likelihood, saying that high probability things are likely. That's just what probability means. And so what I will think of as an optimal strategy for this kind of game is one that just maximizes likelihood in this context that says, given the state, under the expectation induced by the data observed in the state given by the K. That's a maximum likelihood game. We can extend this to Bayesian inference. So we've got now like priors, and we're making predictions given our prior beliefs. And so what we're doing now is choosing a channel which gives us the best observations and also can do a lens which gives us the best predictions and also can do the updating in a good way. And so that says, given all my observations, I want to minimize the average divergence from the exact inversion, given my approximation. That's what this loss function says. Okay, and then since the Bayesian updates compose according to this lens rule, these games are closed under composition 2, so we get this kind of nice property that a composite approximate inference game is like the approximation of a composite inference game. Okay, but computing this divergence is difficult, and so we can do things like various approximations to it, like this one called the free energy, which is quite prominent. And this is just an upper bound on this divergence that ends up, if you write out the equations, to be easier to compute. And it turns out in some situations that if you write out the equations, they look a bit like what neural circuits look like. And so people think, okay, well, that's what the brain does. This is a story we can tell another day. I'm saying this is one way of doing this approximate Bayesian inversion. The question I'm interested in today is, how do we make systems that might be equipped with this kind of model, in some sense, live? How do they then find abstractions? How do they act in the world? Notice I haven't talked about interactive systems at all, just predictions.
Sorry,
observation.
Toby.
Yes, so I'm running out of time. I've got to.
Okay.
What's the question? Hello, Alexander?
I think he ran off. But
okay. I mean, how much time can I take?
Yeah. So Toby, you should consider yourself to be free to take up to 15 more minutes if you need total.
Okay, that should be perfect. Thanks. Okay, so we can talk about the details. We can talk about the details afterwards. I want to get to the end of my story. Okay, so the next step. Okay, I've got this idea about statistical models that might be in the heads of or in the brains of the systems. How do we breathe life into those systems? How do those systems find abstractions? Okay, this is what I'm going to talk about now. I'm going to go back to these polynomials, these boundaries of the systems. Okay, so I drew this box before, this pattern of interconnection. And I said, okay, there are some polynomials and morphisms of polynomials, and that's the interconnection pattern. But the thing is, it's not just boxes and wiring. There's much more to this kind of structure than that. We can talk about all kinds of interconnected systems. And in particular, we can talk about systems with some kind of shape that interacts with some other kind of shape by kind of coupling together, like the enzyme-protein complex that I drew earlier. The enzyme has a shape, the protein has a shape. They come together by coupling, and that changes how they can interact with the rest of the world. And we can talk about those shapes of both the enzyme and the protein and the interconnection and the interaction with the world, all with polynomials. And so that's lovely. Okay, so this is the maths that I sketched verbally earlier, spelled out in a little more detail, not very much because I'm mostly interested in storytelling today. But as I said, a general polynomial looks like a sum of these kind of terms, a sum of effectively these representable co-presheaves. And so I'm going to call a general polynomial P. It's going to be indexed by this P of 1 thing, which we can talk about why it's P of 1 later, but just bear with me on that. And I'm going to call each part of this polynomial, each factor of this sum, P square brackets I. So for instance, in this example above, P of 1 is going to be A plus B plus C, because as I said, it's got A times Y of X, B times Y to the Y. And so we just add up these coefficient types. And so if I is in A, then we have X as the kind of total, the factor of the total space here. And this gives us a bundle. It gives us a bundle over this P of 1 type. Okay, so that's one reason why I was talking about bundles earlier. So I like to think of these polynomials as phenotypes. The base type is the type or the set of configurations or the morphology that the system can have. And then each of these P of I's is the type of imminent signals that the system can receive. For instance, think of a hedgehog. It's going around the world. It receives wind and light and heat on its surface, and it makes judgments about the world on the basis of that. And then, it might get scared, so it curls up into a ball, which means that no longer is its underbelly kind of exposed to the world, and so the type of signals that it's receiving changes because it's changed its shape. And that's the same with all sorts of systems. They have shapes, and the things things that they can do or the sensations that they can receive depends on the shape that they choose. I like also to think that these things formalize Markov blankets because everything comes in through this sensorium, and the system acts by changing its shape. It just acts by changing its blanket, its phenotype, its morphology. Okay, and then as I've said, the morphisms of polynomials model these interactions, just like on the left. And I'm not going to go into this very much, but I'd like to use it later. So we can also assign positions in the world to these polynomials by thinking of the polynomials themselves as depending on positions of some other polynomial using kind of dependent types. And then the kind of base polynomial of this dependence would represent the shape of the world. But yes, as I say, that's a bit much to get into right now. Okay, so we can start to animate these polynomial systems, these shapes now. Because we can index the category I described earlier of statistical games by polynomials. It's like a slice construction, but we effectively slice over the total space of each polynomial. And that says that, and that gives us a category over each polynomial of systems predicting like sensoriums, the sense data that those systems can receive in each configuration. And they might have a belief about their particular configuration right now and the sensations they can receive in that configuration. And we have a category of these things because we might have lots of different kinds of internal model, and we want to think about the morphisms between them and things like that. So we get this index category of statistical games over polynomials. It's a fibration. A fibration is just a categorified bundle. And we could think of what happens if we sample from the predicted configurations, and that effectively says something like, we get something a bit like action because it says, what configuration should I choose right now? And because the index category is a functor on the polynomials, we also get a description of what happens given a polynomial morphism, which is effectively like a description of the generative model of a composite system or a multi-agent system in terms of the component system's models. And so you can think of something like getting a model of the beliefs of something like a corporation, giving the beliefs of the system, of the parts of the system, the people that work within it. Okay, but these things, they still don't do anything. They're just abstract statistical games. We want to sort of breathe life into them. So I have this thing, I stole this word doctrine from David Jazz. I like it, so thank you, David. I have this thing called an active inference doctrine, which is like a recipe for turning polynomially indexed statistical games into dynamical systems. And these give us index functors. And it says, given some statistical game, I can do some dynamical process to optimize my performance at playing that game. So in something like the free energy literature, you get various recipes for doing this approximate inference thing, which give rise to processes of perception and action. Processes by which systems choose their configurations and make predictions about the sensations that they receive from their environment. So these resulting dynamical systems do this perception and action, and then they can, and in doing those two processes, they can bring their beliefs into alignment with reality, whatever that means, and improve their chances of survival or their abilities to find abstractions or their fulfillment or whatever. And so the question now is, okay, what is that whatever? What drives these systems? And I'm going to think of systems with this driving process, this elan vitale, as a kind of as giving systems volition. Okay, so recall that a system's performance at playing one of these games is contextual. It depends on the prior beliefs, and those prior beliefs include the model structure, the particular choice of statistical games, the particular choice of lens, and on the environment. And so to improve the system's performance at playing a game, the system can do four things, which are basically two things. The first is update the beliefs, that's perception. The second is update the model structure, which is a kind of perception. We could think of the latent space of these models as roughly like the space of possible external states. The system can also change its shape, which is like action, or it could couple with part of the world and change that shape, which is like another kind of action. I could go along to you and poke you and you might do something. Okay, and so by equipping the system with strong, like internal beliefs, like beliefs with low variance around a particular state, we can give it preferences for those states. And then the system will attempt to achieve those states. And in doing so, display something like volition. Okay, so we could sketch a couple of examples of this, starting back with the biological systems that I was talking about earlier. A nice simple one is homeostasis. So suppose that the system sensorium includes a key parameter, like the ambient temperature, that it needs to maintain in a particular range for its survival. And then suppose that by adjusting its configuration, the system can move around to sample this parameter, and that the prior given to this system encodes a high precision or low variance distribution centered on this acceptable range of the parameter. And so then if it's playing a free energy game and it's given a dynamical system which does minimizing free energy, the system will attempt to configure itself in such a way that it remains within this acceptable parameter range. And we can think of that as like homeostasis. I don't have time or space to give you all the details, but it works something like that. And we can, if we think that we've got multiple of these systems that's doing this homeostasis thing or obtaining some desired parameter configuration, we can think of morphogenesis. And now let's think of this parameter as like some signaling molecule in the environment. The map of polynomials encodes the pattern of signaling molecule that is received by each system, given the configuration of the rest of the systems. And suppose that the priors of these systems encode target local configurations, like the preferences of what's near me, around me. And then doing each of these things, doing free energy minimization, induces the systems as a whole to arrange themselves to obtain some like global target pattern. And we can think of this as forming a particular composite morphology, morphogenesis. We can also use this language to talk about the world inside the mind of a system. We can use this to model like navigation of this world. So these worlds can be like arbitrary spaces. So we can if we attach these polynomials to positions in some world, that world could be anything. It could be the topos that I started talking about earlier. And there's no need to restrict the type of thing that the type of object that the latent space of the internal model is. And it too might be structured like a topos. And we could think of the parameters of this model as encoding the structure of the topos that the system expects to be out in the world, the context or the shape of the world. And then updating the model parameters means moving around in this base topos, means learning what maps to where in the world, given the context. And then the state representation that the system has in mind says, where am I in this abstract or this relatively abstract or more or less abstract, this real, or I don't care, this space. And action corresponds to moving around the space, following a morphism in the topos. And then you could think of there being some sense data, I don't know what that is, and it would vary corresponding to this action in a nice vibrational way. And putting a prior on a particular location, particular object in this topos would induce the system to reach that location, learning the structure on the way. And in particular, if I'm trying to do some kind of mathematical proof, I have a particular place I want to end up with loosely defined. And I'm trying to navigate myself towards it. And this then says to me, okay, well, navigating a space is really just like finding a mathematical proof. And sort of abstractly, there's no reason we should think of them as much different. And I like to think that this points towards something like a well-typed theory of cognition, where actions correspond to like applying morphisms, and we can change the structure of the space by applying morphisms. And there are some nice universal morphisms we can use, and we can talk about what happens if I make an action using the internal HOM of the Cartesian closed structure of the topos. Loads of stuff to talk about. And in particular, we could do things like use the internal logical language to put logical constraints on the target state to say, these states, these locations in the topos, they're dangerous. Don't go there. Or more complicated propositions that involve, dependence or implication or quantifiers. It doesn't matter. We can use this internal language to say, prefer these these propositions to hold and not others. But for the precise details of how to do all that is kind of left to figure out. But I still think that, I mean, it's a direction to me that seems promising. So I will wrap up at this point. It seems increasingly natural to me to think of the world inside my own head like a topos. Structure learning, finding abstractions, becomes kind of like a logical context learning. My brain seems to assign beliefs to propositions. It acts like a kind of classifying object. And we could represent beliefs about processes using the internal Cartesian closed structure. And we could do things like ask, how do different systems' internal universes compare? Do they have similar beliefs about the context? Do we have consensus? If not, what are the abstractions? I'm really keen to connect up with the stuff that David was talking about last week in this respect. And then to me, finding the right abstraction seems to me something like finding good explanations. In our world, more often than not, they do seem to be compositional and hence reusable. Poetically speaking, that means something like finding compelling stories. And notice that good, compelling stories are the ones that hang around for the last a long time. Those are both ancient stories, like, epics from long ago, as well as mathematical stories, like the right descriptions of things like spaces. But I do want to emphasize that in a complex world, notice that all these statistical games, the performance really depended on this context information. And again, the logical statements that you can make in a topos really depends on the context. So considering systems in isolation is not helpful. We should always ask, what is the context? What things are connected to me? Okay, and of course, there's loads left to do. Among other questions, to what extent does this process by which we or our brains find abstractions, the process that I've begun to sketch today, agree with the kind of mathematical descriptions of things like abstraction in terms of concepts like black boxing or hierarchical planners and other accounts? What's missing? How do we relate them? I don't know. How do they relate to causal or temporal inference? Can we see explicit signatures of the kind of cognition that I'm pointing out in the brain itself, its compositionality, the kinds of representations that are required? How, if we can, do we use the internal language of this topos, that is this internal universe in my head, to encode constraints on the behaviors of active systems, possibly like AIs, but also including corporations, or or if we're interested in biological design, it's a similar thing. And then, how can we compare systems' internal universes? How do I know that the stuff that you see or your explanations are compelling for you? How do I know that what you find compelling is the same as or related to what I find compelling? And how do I know that our stories really kind of resonate? I think we've got mathematical tools to answer these questions, and really it just amounts to sort of applying them. Although of course it's easier said than done. But that's all I'm going to say today. So thanks. I should have written thanks there, but I didn't. That's my talk.